Okay, well, hi everyone. Thanks for that introduction. My name is Natalie. As you mentioned, I did my master's work with Dwayne Beck, South Dakota State University, specifically at Dakota Lakes Research Farm, and I'm happy to be here and talk a little bit about that research and just kind of some general no-till themes. So they put me right after lunch, and I start with a very brief history lesson, so please don't fall asleep on me. There won't be a quiz, but if I see people napping, then there will be a quiz. So throughout history, there have been declines in soil fertility and erosion in many civilizations. So from the Mayans to the Greeks and the Romans, right? Every civilization has had some issues with their soil. And of course, the Roman Empire didn't collapse just because of soil erosion, but poor farming practices and the inability to feed their population definitely left some empires susceptible to other issues like invasions or plagues, things like that. So all throughout history, civilizations have either perished or moved on and conquered new lands, right, to find fresh new soil that hadn't been broken yet to continue surviving. And I guess I want to ask this question, how many of these empires survived, right? So we can either, sort of perish or move on and conquer and find new soil. Wanted to read this quote by George Washington to Alexander Hamilton in a letter in 1796, so just when the U.S. was still a pretty brand new country. George Washington said, "A few years more of increased sterility will drive the inhabitants of the Atlantic states westward for support. Whereas if they were taught how to improve the old, instead of going in pursuit of new and productive soils, they would make these acres, which now scarcely yield them anything, turn out to be beneficial themselves." And within 10 years of that letter, Lewis and Clark were exploring the West, trying to find new lands for the country to break open and produce food for Americans. And this picture was taken at Dakota Lakes Research Farm right along the Missouri. This is just east of Pierre. But regenerative agriculture at its core really is this idea of mimicking natural systems. So farming is not completely a natural system, but it's a managed system operating within natural systems. So in regenerative agriculture, we try to mimic those natural systems, and we do that by fixing cycles. So the water cycle, nutrient cycles like nitrogen and phosphorus, the carbon cycle, things like that. And so for sustainable food production, these cycles must be restored. They must be regenerated, right? Right now, we kind of just have this input-output system where everything is sort of linear, and we put things in, and the soil blows, and then we take our hay off and send it to China and all this stuff. And so we need to kind of try to fix these cycles if we're going to keep farming on this land and sustain our population. So Dakota Lakes Research Farm was initially founded to study a lot of things, and first was specifically the water cycle and to try to fix the runoff issue on their irrigated ground. And of course, the answer to that ended up being no-till production. And so I wanted to just show these videos here. This is a very scientific rainfall simulator that we built. It's a windshield wiper motor spraying water on a ladder onto a piece of ground. And we put on 4 inches of water in about 10 to 12 minutes. And on some of our fields, we got 0 runoff. All of it infiltrated into the ground. So no-till at Dakota Lakes was very successful in helping to fix that broken water cycle. And of course, we're all here today, right, because no-till is widely promoted as a soil health and conservation practice. You see a lot of NRCS, USDA, all these things about minimize disturbance. But no-till alone may not be enough to restore and regenerate soils and agroecological cycles. So these pictures are all from Dakota Lakes. They were all taken in the same summer. Dakota Lakes has been no-till for over 30 years now. And I think we would all agree that those top 2 images probably are not the highest quality soil, right? You can kind of see sort of that platiness of a soil, right? It's really hard for water, air, and roots to get through each of those individual little plates. Those are also more susceptible to erosion and water runoff. And then those bottom two images, I think we would all pretty much agree that those are sort of healthy soils, right? They're that dark, crumbly, you can see those aggregates, the soil kind of clumped together, considered kind of like that chocolate cake type look, right? Like that's kind of what we're aiming for. We know there's a lot of biological activity, a lot of organic matter, a lot of water and air movement, and so that's kind of the goal. The only difference between all of these pictures is the crop rotations that they've been under for 30 years. So they're all no-till, but the crop rotations have been different. So to truly pursue soil health, a shift in tillage management must be accompanied by a shift in crop rotation management as well. You can't just change one or the other. The two have to go together in order for soils and yields to be maintained and improved. Okay, so I want to talk about my research at Dakota Lakes, and so my main question was, how do crop rotations impact soil health and crop yields under 30 years of no-till management at Dakota Lakes Research Farm? And this was a really fun project to work on because a lot of folks had, and I'm sure some of you have seen visually the differences, right? You visited Dakota Lakes, you've gone around and walked with a shovel and seen those differences. But nobody had yet really quantified those differences. And scientists, policymakers, funders like to see hard numbers, like to see the actual real numbers. And so that was kind of my role, is saying, let's actually define these differences. So before I get too much into my research, I want to just define some terms that we could use to talk about crop rotations, just to kind of get everybody on the same page. So we can think about diversity and intensity when we think about crop rotations. So diversity is referring to the crop species that are in rotation, and of course you want a combination of crops that complement each other, reduce pest pressure, increase profitability, all those things. Intensity then is referring to water use of that rotation. And the goal here is to match the crop water use with the soil water storage under a given climatic condition. And so that's going to vary, of course, wherever you're at. And then in terms of how we can kind of break our crops into these different categories, we have the grasses and the broadleafs, and so within those we've got warm season and cool season, and those kind of all get at that diversity piece, and so you want kind of a mix of all that. And then the higher versus lower intensity, our warm season crops tend to be higher intensity, right, using more water, and then the cool season crops tend to be a little bit lower intensity, using a little bit less water. On some of my slides, I have a diversity index number, and this is just kind of a formula that accounts for the crop types, the crop intervals, and any conflicts in seeding and harvest. And with the diversity index, a higher number is more preferred, is a better diverse rotation. Another way to think about crop rotations is through the residue production and how much residue the crop leaves behind after harvest. So all the grasses, corn, wheat, sorghum, those can be considered high residue, right? And then the broadleafs would be lower residue. So here are some pictures of, those high residue crops. When I first got to Dakota Lakes, I thought there was too much residue. I thought it looked messy and like there was too much trash on the field, and I was like, what the heck is wrong with this? There's too much carbon out here, there's too much biomass. But as I came to learn, and hopefully we'll present through these slides, that residue is actually really key, and that huge amount of residue is actually probably one of the best things that happens at Dakota Lakes. And then just for example, I tried to show a picture of soybean residue, but that doesn't really exist. So there's the soybean residue, which is just bare dirt. Okay, at Dakota Lakes, we've got irrigated and dryland rotations. Start with explaining the irrigated. So first we've got just our typical corn-soy rotation. That diversity index, it gets a -2. It has 2 crop types. It's not very diverse, and only half of the crops, 1 out of 2, are high residue. Then we've got a corn-corn, soy-wheat-soy rotation, which is a bit more diverse, and it can be considered to have 60% high residue. So 3 out of the 5 crops are high biomass producing crops. Somewhat recently, they added a corn-corn, soy-wheat rotation, which is about the same diversity, but kind of bumps up that residue production, so that's our 3/4 high residue. And then finally, we have the continuous corn. There's been a field that's just been in corn for 30 plus years. Dwayne likes to say longer than I've been alive. And while that is a super high residue system, it has zero diversity, right? And so there's some kind of interesting comparisons we can make there. Okay, on the dryland side then again, we've got wheat broadleaf, corn broadleaf rotation, again, that 50% residue. This one's pretty high diversity though, right? 4 different crops, we can do lots of things there. Then we've got a wheat, corn broadleaf, 67% high residue, still fairly diverse. Wheat, sorghum, corn broadleaf, this is our highest residue actual rotation that isn't a monoculture. And then recently, there's been some work to try to incorporate perennial sequences into the rotations. And so I have some data after 5 years of switchgrass going into winter wheat production. Okay, since soil health is kind of a buzzword, I just want to provide a definition that I use to think about soil health, and that's the capacity of the soil to support life, produce food, feed, fuel, and fiber, and perform agroecological functions. And for me, I think of soil health as just a piece of this whole puzzle, right? We need healthy soils that function well in order to restore those broken water, nutrient, and carbon cycles. So I've looked at a few different properties, soil health properties in my research. First is chemical properties, so things like pH, all your nutrients, calcium carbonate, organic matter, all those things. Organic matter kind of fits into all 3 of these categories though. Biological properties, I looked mostly just at microbial biomass, so just kind of the amount of fungi and bacteria that are in the different soils. And then physical properties. So that kind of gets at that platy versus granular or crumbly structure. Other physical properties were like the infiltration and then runoff and erosion. So just to give you an idea of the kind of data that I'll present, I did some deep soil sampling in our dryland systems. Those refer to the chemical properties and bulk density. And then did some surface soil sampling for some interesting biological properties as well as aggregate size, which gets at that crumbly versus platy. Okay, starting with some biological properties, I want to take a second just to kind of orient you to this graph. There we go, here's the laser pointer. Okay, so on the x-axis, this bottom axis here, we have rotation. I put the irrigated rotations first, and then the dryland. And then I've also included their percent of residue production, or how many crops in the rotation are high residue. So we start with the corn soy at 50% and work all the way up to the continuous corn at 100%, and then do the same thing with the dryland. The last column here is that 5 years of perennial switchgrass followed by a year of winter wheat. So we can see, and then, the y-axis here, what this is actually measuring is just that total microbial biomass. So how much of a microbial population is there? And there were really few significant differences in total microbial biomass among crop rotations. It's really hard to measure biological properties, and so we weren't like super surprised to not see any differences because it's hard to get at those biological differences. But where we did start to see some differences was with fungal biomass specifically. And we found that there was an increased fungal biomass with increased residue proportion in the irrigated rotations. And so, again, point you to the 60, 75, and 100% rotations. Definitely much higher fungal biomass compared to that corn-soy rotation. We like fungi because they help us to access more water and nutrients for our plants. We didn't see any differences in the dryland, in the deeper depth. And similarly, we found pretty much the same result. We had increased arbuscular mycorrhizal fungi with increased residue proportion in those irrigated rotations. The AMF, or that arbuscular mycorrhizal, those are the ones that form that symbiotic relationship with plant roots. And then finally, this gram-positive to gram-negative ratio. This is essentially just a measure of whether or not a microbial community is stressed or not. So if there's a high gram-positive to gram-negative ratio, that microbial community is under some kind of stress, probably a water stress. And interestingly, the 50% high residue rotation, so the corn, soy, and the wheat broadleaf, corn broadleaf, had a higher gram-positive to gram-negative ratio. So something is causing a stress on the microbial communities in those rotations. Okay, moving on to some chemical properties. So first starting with pH, again, just to kind of orient you to this graph, this is for the dryland systems only. We start with the 50% high residue rotation, which is that wheat broadleaf, corn broadleaf, and move up to wheat, corn broadleaf, wheat, sorghum, corn broadleaf, and then we had some different switchgrass treatments. So 5 years of switchgrass and then 20 years of switchgrass. The different colors are indicating the different depths. So the lighter depth is kind of that first 0 to 6 inches and then continuing throughout the profile. And we can see that the 67 and 80% high residue rotations had a higher pH than the 50% residue rotation. Also, the perennial sequences increased soil pH. Now, we don't really have an acidity problem at Dakota Lakes right now. I mean, even our lowest pH is still hovering around 7, so we're not really too concerned about it. But this principle that crop rotation and or perennial incorporation can change pH could be really important in some areas that are starting to see soil acidity problems. So I'm out at Pullman, Washington. Eastern Washington right now is seeing really severe soil acidity issues. Like, I'm talking pHs in the 4s. It's really bad. And so this idea that we have to rethink our crop rotations and maybe even incorporate some perennials, that could help to increase those pHs without maybe having to spend tons of money on lime. Then this graph is kind of the exact same layout, but just with calcium instead of pH. Our thinking here was that the deep roots of the perennial switchgrass are bringing up calcium deposits from deeper down into the soil up to the surface and kind of doing the liming process just sort of for free, right, for the cost of seed. And so we can see those calcium concentrations are definitely increased in 20 years of a perennial compared to the other rotations. Then in the surface sampling, which included both irrigated and dryland, we found that the continuous corn and the dryland alternate year broadleaf have the lowest pH. Again, it's not acidic enough to cause problems, but just good to know. The reason that the continuous corn probably had that low pH was it's fertilized with nitrogen every single year, and nitrogen is kind of an acidifying agent. But again, I do want to note that even after just 5 years of that perennial switchgrass, we were actually able to increase the pH compared to another rotation. So it's just a little over 6, and then we increase it closer to 7 pH after 5 years, which I thought was pretty exciting. Okay, organic carbon, another super hot topic these days. So this graph is from dryland deep sampling. So we went down to 120 centimeters, a little over 3 feet. And we've got organic carbon as a percent on the y-axis, and then again I've got labels for the residue on the x. And the increased proportion of high residue crops increased organic carbon contents. This does make sense, right? So your high biomass crops like wheat or corn, they have they produce a lot of organic matter, and organic matter is made up in large part of carbon. So the more carbon crops that we have in the rotation, it makes sense that ultimately over time that would increase the soil organic carbon. And we do see this kind of really nice linear trend as we increase high proportion of high residue crops, we're also increasing our organic carbon. Interestingly, we didn't see a significant increase in organic carbon after 5 years of a perennial. Again, sometimes it's difficult to measure those differences. And then looking at both irrigated and dryland, just kind of at that surface level, again, we see a really nice linear trend as we increase those high residue crops in the rotation. We're also seeing an increase in organic carbon. And again, there's just kind of this mixed impact of organic carbon after 5 years of a perennial. Oops. There we go. Organic matter, as I mentioned, organic carbon is a big component of organic matter, so it makes sense that our trend is kind of similar. So there was a slightly increased soil organic matter in the 67 and 80% high residue rotations compared to that 50%. And again, the organic matter in the perennials was higher as expected. This is that surface irrigated and dry land systems again, and just a really clear linear increase in organic matter as we increase those high residue crops in rotation. All right, physical properties, starting with bulk density, which was just done in those dry land rotations. And the rotation that had 80% high residue crops had a slightly decreased bulk density compared to the other rotations. Bulk density, you can kind of think of as the amount of soil in a given area. And so when we have a well-aerated, soil with lots of pores, a good pore network, we're going to decrease our bulk density. And so that's kind of what we want to see is those lower bulk density numbers. And that 80% rotation did that. Okay, aggregate size. So I spent a lot of time one summer with a giant mechanical sieve. I should have included a video in here, but it's like really loud and obnoxious. And anybody who was at the farm that summer would tell you they probably didn't like me very much. But what I was able to do was separate out aggregate sizes, so those little clumps of soil, into different sizes. The larger aggregates tend to be less susceptible to erosion, right? If I've got a decent clump of soil, it's probably not going to blow away in the wind, whereas those tiny little soil aggregates are way more susceptible to erosion and runoff. The larger aggregates also tend to indicate that there's a better pore network, better continuity in our pores in the soil. And I found that there is an increasing aggregate size with an increasing proportion of high residue crops in the rotation. So we're increasing organic carbon, and we're also improving that soil structure, having larger aggregates. And that goes back to that picture that I showed at the beginning. Macroaggregate proportion is just another way to think about aggregate size, and so this is saying like what proportion of the soil is those larger aggregates that aren't going to erode away. And again, we see that exact same trend. So the more biomass that the rotation is producing, the better its soil structure is. Okay, to kind of summarize some of these soil health findings, I made just kind of general table, and it's just this kind of like pitting the different rotations against each other. So a rotation scores a point if it has an improved soil health property compared to one other rotation. So for example, corn soy didn't have a greater fungal biomass compared to any of the other rotations, but that corn, soy, wheat, soy rotation had a higher fungal biomass when compared to two other rotations, so it gets a 2. And we can tally all those up, and we see that the 3 bottom rotations, so any rotation that was 60% or greater high residue crops, scored much better and sort of outcompeted that traditional corn-soy rotation in terms of soil health. Yeah, there it is. So rotations with 60% or greater proportion. And then did the same thing with the dry land, and so this first table here is that surface sampling, and then the second table is the deeper sampling. And once again, the 67 and 80% high residue rotations outperformed the 50% residue rotation. Okay, and it's not just all about soil health, right? If I can't grow a good yielding crop, I'm not going to make money. So it was really important for me to also include some crop yield data in this as well. So for the irrigated systems, I'm going to talk about corn specifically, and then for the dry land, I'm talking about winter wheat. And then just as a reminder, these are the rotations here again. I looked at data from the most recent 20 years of Dakota Lakes. It takes some time, right, for a rotation to kind of equilibrate and stabilize. And so the first 10 years of yield data were kind of all over the place. And so I picked the last 20 years. And that's also when we actually started having digital records and we hadn't lost a lot of data. Okay, so starting with some irrigated corn yield results. So this is a yield graph just over that about 20-year period. We've got the corn soy, first year corn of that 5-year rotation, second year corn of the 5-year rotation, and then continuous corn. And then we've got yield in bushels per acre on the y-axis here. And I just want to kind of point your attention to that first year corn of the corn, soy, wheat, soy rotation, significantly higher yield than all of the other rotations. And then these are the actual numbers here. So we see that the first year corn of the 5-year rotation had the highest mean yield, followed by corn, soy, followed by the second year corn of that 5-year rotation. Another way to think about yields is to compare them to something that's called an environmental mean yield. So that's creating sort of one data point, or in this case, this whole axis of the year mean yield. So across all the rotations, each year gets a yield, and this was the average yield for that year for all of the rotations. And then I've got the yield specifically for each rotation right here. And just kind of want to point out, since it's a little bit hard to see, that first year corn of the 5-year rotation is those dark squares here. And it is consistently out yielding everything else. The soy corn is only out yielding that 5-year rotation in about 4 out of 17 years that I had data for. So another way to put that is 3/4 of the time, first year corn of the 5-year rotation is the highest yielding. Looking at dryland winter wheat, we've got wheat broadleaf, wheat corn broadleaf, winter wheat sorghum, corn broadleaf, first year wheat, and then the second year wheat of that rotation. And over about a 15 to 20 year period, the wheat corn broadleaf had the highest mean winter wheat yield, followed by that first year wheat of that longer rotation. And again, kind of do this same kind of comparing against the environmental mean. The wheat broadleaf, corn broadleaf rotation out-yielded the wheat corn broadleaf in only 5 out of the 14 years that I had data for. Another way to put that is 2/3 of the time, the wheat corn broadleaf was the highest yielding. To put this within maybe an easier to think about context, these are yields for a hypothetical 5,000 acre farm if we had our irrigated rotations that were at Dakota Lakes on a 5,000 acre farm. And so for corn soy, we get about 500,000 bushels of corn, 150,000 bushels of soybeans. But I really want to compare that to this 5-year diverse rotation. So overall, we're getting a little bit less corn, right? But the exact same amount of soybeans, if not a little bit more, plus we have that year of winter wheat in there too. So we're maintaining our productivity pretty well, but then we've also got that added sort of diversity and stability of having that extra crop in there. And this is the same thing but for the dryland yields. And again, I just kind of want to show this to you to show that, adding that diversity really helps to spread out, where your income is coming from. And you can do that without really taking a yield hit on some of those key crops. I believe these are in your handouts too, in those folders as well. Okay, so just to kind of summarize and put together those soil health and yield results, kind of side by side. We'll start with the irrigated rotations with that corn soy, yielded about 198 bushels on average, but the soil health improvements over other rotations was only 2, so not great. Then when we compare that to the diverse rotation, right, that corn, soy, wheat, soy, we're improving our yield in the first year, maintaining slightly decreasing yield in the second year corn, but we also have much better soil health or soil quality in that rotation. So we're able to make those improvements to the soil while also improving the yields too. And this is where this idea of balancing both diversity and residue production comes into play. So when we compare the diverse rotation to the continuous corn, that continuous corn rotation had a great soil, really high organic matter, good crumbly, chocolate cake structure, but it just doesn't hold up with the yields, right? We all kind of know a monoculture corn on corn, it just doesn't work over time. So we need to balance having both that residue production for the soil while also having the diversity piece to maintain our yields and to deal with other issues like pests. Similar principles kind of apply to the dryland situations as well. So that alternate year broadleaf, or the 50% residue over here, only had 3 improvements in soil health compared to the other rotations, and it also had pretty poor yields, and those yields were really variable too, which is kind of an issue at times. And then, comparing that to the wheat corn broadleaf and that long diverse rotation, they had enough residue to be improving the soil and making that really healthy soil, while also really maintaining and improving winter wheat yields as well. So I also want to kind of make this point that crop rotations change soils over time, right? This happened over 30 years at Dakota Lakes. And so there's a little bit of need of patience, right, for some of these changes to occur, but there's also really a need for these long-term studies. It's really rare to find a place like Dakota Lakes that's been researching these systems for 30 years. And so that's kind of a call that I have to you all is, on any sort of boards or things you get asked about. I think it's really important that we fund this long-term research to try to get at some of these things that take time to occur. I think there's also a need for changes to crop insurance and farm bill policy to reduce barriers to adopting new crop rotations. It can be hard to try something new if it doesn't totally fit into what your crop insurance or the subsidies are telling you. And so there's definitely some work that needs to be done there to try to reach some of these goals that we have for soil health and yields. Yeah, so just to end, I just want to say it's not just the no-till. We have to have that crop rotation piece too that goes along with the no-till. To improve soil health and to increase crop yields, we kind of have to have that high residue as well as rotational diversity as well. So with that, feel free to reach out to my email, and I'm happy to take any questions. Yeah. Yeah, okay, so the question was for the continuous corn, is it closing the yield gap, kind of comparing it to the other rotations after 30 years? So yeah, really good question. The last year, the second summer that I was there, pretty hot and dry, the continuous corn yield was just as good as the corn soy yield. They were very similar. And so as time has gone on, those healthy soils in that continuous corn are really helping it to be more resilient to some of those stressful years. So we're seeing it kind of creep up towards the other rotations. Yeah.
In your 20-year switchgrass, they improved the soil pH. Is that with switchgrass removal?
Yes, sometimes. I don't know for how long they were removing it. We were taking it off when I was there, so there's a little bit of removal, yeah. But that's a good point. So taking off that switchgrass does remove some things too, yeah.
It was hay, it wasn't grazed.
Both. Yeah, both. All right, well, thanks, everyone.